Hello guys, my name is Michael Avashit Reddy, pursuing my BTech at Institute of Aeronautical Engineering. Today we are going to be discussing about ending null pointer crashes, the role of void safety in programming. So before we dive into the video, let me introduce what are the topics we are going to be discussing and a short intro about the topic. Void safety plays a critical role in modern programming languages as it directly addresses one of the most common causes of software crashes and bugs. Null pointer dereferences in languages like Eiffel, void software safety is integrated into type system, which ensures that variables must be explicitly defined to have a null, not null value. This eliminates the ambiguity of null references and helps developers avoid runtime errors that can arise from dereferencing null pointers. The historical context of implementing void safety can be traced back to frustrations expressed by prominent computer scientists like Tony Hoare, who coined the term billion-dollar mistake to highlight the economic impact of null reference errors in software development. By promoting a rigorous approach to type safety, EFL and other languages with similar features aim to enhance software robustness and reliability. So, in short, we can classify such type of errors as a billion-dollar errors because in software industry when and dealing with such errors can lead to undesirable output. So it is very important to ensure the crashes caused by null pointers and void safeties. Uh, so here is the quick review of what we are going to be discussing tonight or today. Understanding null pointer dereferencing, the billion-dollar mistake, Eiffel's approach to void safety, the mechanism of void safety, challenges and continuous improvements. So let us discuss about how to dereference a null pointer. Null pointer dereferencing is one of the most frequent sources of bugs in software developers, often resulting in crashes that can interrupt applications performance and decreases user satisfaction. When a null pointer is dereferenced, the program may try to access memory that is not allocated, leading to exceptions which terminate the program unexpectedly. Many programming languages like C and C++ provide the concept of null pointers but lack built-in mechanisms to enforce checks the prevents their usage in operations, making it a responsibility of the developer. In contrast, languages like EFL introduced structural rules that enforce non-nullable types, ensuring that variables are properly initialized before they are used. The prevalence of null referencing errors has led to various programming practices and patterns such as using optimal types or null object patterns to mitigate risks associated with null pointer dereferencing. Tool support for detecting null pointers dereferencing has evolved with static and dynamic analysis, tools becoming essential for identifying potential issues during software development. Tony Hoare's characterization of null pointer dereferencing problem as billion-dollar mistake. So now we are going to be talking about what is the million-dollar mistake and how referencing null pointers shall lead to a billion-dollar mistake. Billion-dollar mistake underscores the substantial economic impact associated with software failures caused by this issue, which has affected countless applications across various industries. stress. The term reflects the costs incurred due to debugging, patching software, downtime, and loss of customer trust, as well as potential legal rep- repercussions. For software companies that fail to manage this risk effectively, research indicates that null pointers exceptions are among the leading causes of system crashes, which can disrupt user and affect productivity in both consumer and enterprise software. As a response to preservance nature of null pointer issues, many organizations have implemented rigorous testing and code reviews to identify and fix potential dereferencing errors before code deploys. The preference the prevalence of null pointer vulnerabilities in security databases highlight the importance of addressing these issues in development process, as they can also be exploited by malicious actors to cause denial of service attacks. In an effort to eliminate such mistakes, modern programming programs are increasingly focusing on safety features and type systems designed to prevent the use of null references, paving the way for more reliable software development practices. So let us see how AFL approach this problem. In AFL, attached types of are defined as types that cannot be null, meaning that any variable declared as attached must be assigned as a valid reference before it can be used, thus eliminating potential for null pointer dereferencing. Conversely, detachable types are types that can hold a null value, allowing for greater flexibility in certain situations, but they require explicit checks before dereferencing to check safety. AFL's type system enforce rigorous rules that compel developers to think critically about object ownership and lifecycle management, leading to clearer and more manageable code. By leveraging compile time checks, the AFL compiler can catch errors related to null dereferencing before the code is run, significantly reducing runtime errors and improving overall software reliability. Static analysis tools complement the type system by analyzing code for potential violations of void safety rules, helping developers identify areas of risks before the system is deployed. AFL's approach to wide safety has influenced other programming languages, inspiring similar feature in newer languages, which also aim to mitigate null pointer issues through stricter type systems and safer code products. Mechanism of void safety. Type declarations in AFL are critical as they explicitly specify whether a variable can hold a valid object or a null object, which lays the foundation for enforcing void safety throughout the code base. Certified attachment patterns establish conventions that dictate how objects are bound to variables, ensuring that any attached variables are guaranteed to reference a valid object before any operations perform. The formal model of void safety provides a robust framework that mathematically defines rules and principles governing non-null references, making it easier to validate program correctness. Mechanized proofs are utilized thoroughly, verifies the void safety rules are applied correctly across the code, potentially catching issues that coding practices might overlook. By adhering to established wide safety rules, developers can create safer programs that are less prone to runtime crashes related to null pointer dereferencing, boosting users' confidence and system reliability. The implementation of word safety in Eiffel inspires ongoing research in programming languages, leading to innovations in type systems and techniques aimed at mitigating the risks associated with null referencing in system development. One significant challenge in implementing void safety in legacy systems is that existing code may extensively rely on null references, making it difficult to refactor without introducing new bugs. Developers often face resistance to change from teams accustomed to traditional programming paradigms, necessi- necessitating comprehensive training and clear documentation to ease the translation to void safety practices. The gradual adoption of void safety features in modern programming is guided by desire to retain compatibility with existing code while introducing safer constructs, a balance that can complicate language design. Continuous improvements are made by encouraging community feedback and collaborations, which helps to identify main points and pain points, also areas for enhancement in void safety implementation across various platforms. Research and development around void safety include exploring advanced inference methods that could automate the identification of potential unsafe code patterns without imposing extensive type annotations on developers. The ongoing engineering efforts aim not only to enforce safety but also to ensure that the programming experience remains intuitive and productive, promoting both robust software development and developer satisfaction. So, let us wind up this topic by the significance of void safety extends beyond just preventing crashes. It fosters a programming culture that values reliability and robustness, encouraging developers to write cleaner and more maintainable code that prioritizes safety and reduces the likelihood of runtime errors, thereby enhancing overall software quality. So let us recap all these topics one by one, starting with understanding null pointer dereferencing. So what happens is in mainly in game development, when a character is abused to be point to a null value, then this pointer is invalid. Or let us say if we are using a recursion where a pointer points to a stack which is not existing in the recursive stack, then such pointers are also called as null pointers. So it is best to avoid such pointers. That is what the Eiffel's approach is saying. Instead of using such pointers, why not avoid such usage of pointers? You can see that in some of the game development examples like Pac-Man and Link Adventures, many of when the Pac-Man goes out of the box, it is pointing to a null value, so that many of the barriers are preventing the Pac-Man to enter such values, so that the pointer shall be pointing to a valid set of values. And talking about billion-dollar mistakes, let us assume that we are playing a game of Pac-Man and the Pac-Man is referring to a pointer which is not existed, or it is just pointing to a null value. In this case, the Pac-Man will the Pac-Man character will not be existed from the game, and it will be a huge deal for a programmer to debug such kind of errors. So what Eiffel approach says is Why not avoid such usage of the such kind of null pointers so that it ensures void safety? But many of the cases, like many of the open world adventurer games like Grand Theft Auto, and many of the not only gaming applications, let us say applications involving dynamic space arrangement, always prone to null pointers. So to avoid such null pointers, there must be, you know, a static space which acts as a dynamic space. Let us say we have an array which will be continuously storing our values. So instead of dynamically arranging value one by one, why not say, let us attach this array to a stack where stack cell stores the values and accordingly stores the value in an array. The same implementation is done in banking applications also. So tackling null pointers is a very huge task, but if tackled very cleverly and efficiently, can lead to a more interactive and also more efficient applications. So here is the quick recap of what we have discussed today. Until then, I will be back with another video. Until then, goodbye.